Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Before we jump into today's topic, a quick vocabulary note. You'll hear the term chunking. That just means splitting documents into smaller, searchable pieces. Turning IT knowledge into career opportunities. A financial analyst uploads a 100-page commercial lease. She asks the AI a straightforward question: what are the termination clauses? The system retrieves a highly relevant passage, and the model produces 3 confident bullet points. But there's another condition in the surrounding section that changes how termination works. The answer isn't necessarily wrong because the model failed. The retrieval pipeline may have given the model a relevant fragment without enough surrounding context. That's the problem we're solving today. Small chunks can be excellent for finding precise matches, but the context needed to answer correctly may be larger than the chunk that matched the query. Parent-child retrieval separates those two jobs: search with smaller chunks, generate with larger context. By the end of this video, you'll understand one of the most important trade-offs in RAG. The best chunk for finding information isn't always the best chunk for answering the question. You'll see how parent-child retrieval solves that problem. We'll break down the architecture, see how to implement it in Python and Dify, then move beyond the demo into the production issues that actually matter: parent boundaries, duplicate results, overlap, storage, embedding consistency, and evaluation. By the end, you'll know not only how parent-child retrieval works, but when it's actually worth using. Here's one of the fundamental problems in RAG. The best chunk size for retrieval isn't always the best chunk size for generation. Small chunks tend to represent focused ideas. That can make them easier to match against a specific query. But make them too small, and the retrieved passage may be missing definitions, exceptions, or surrounding context. Large chunks preserve more of the document, but they may contain several ideas at once, which can make precise retrieval more difficult. So we're balancing 2 goals: retrieval precision and generation context. Parent-child retrieval gives those jobs to different chunks. Search the smaller child, then return its larger parent. That's the architecture. Here's the playbook. Take your document and split it into big parent chunks. Think full sections or meaningful units like a contract clause. Then, inside each parent, cut smaller child chunks that are precise enough to match a specific query. The parent is the context unit. The child is the precise search target. This 2-level split is the entire architecture. Everything else is plumbing. Quick check. Parent-child retrieval finds a highly relevant child chunk. What happens next? Does the system send only that small child to the LLM? No. It uses the child's parent relationship to retrieve the larger parent context. Remember the pattern: search small, return larger context. If you remember that, you understand the core idea behind parent-child retrieval. Here's the parent-child architecture in one picture. Your document is divided into meaningful parent sections. Inside each parent are smaller child chunks. When a query arrives, the vector search operates on those children because they're smaller and more focused. But the child isn't necessarily what we send to the LLM. When a child matches, The system follows its parent ID and retrieves the larger section it came from. So remember the division of responsibility. The child is the retrieval unit. The parent is the context unit. Or even simpler, the child helps us find the evidence. The parent helps the model understand the evidence. That's the architecture. But there's an important catch. A larger parent doesn't automatically mean better context. The parent itself has to be well designed. And that's where we're going next. Let's lock in the architecture before we build it. The child has one primary job: help us find the right information. The parent has another: give the model enough surrounding context to understand that information. So think: child, retrieval unit, parent, context unit. That's the key distinction. The best unit for search doesn't always have to be the same as the best unit for generation. And once you separate those two responsibilities, you have much more control over your RAG pipeline. Parent-child retrieval doesn't automatically fix bad chunking. Imagine a contract definition starts at the bottom of one parent chunk and finishes in the next. You may retrieve the correct parent and still give the model incomplete context. So parent boundaries matter. When the document has reliable structure, use it. Headings, sections, clauses, paragraph groups, or other meaningful document units. If the structure is weak or inconsistent, semantic splitting can also help identify natural boundaries. The goal isn't always use semantic chunking. The goal is make each parent a meaningful, reasonably self-contained unit of context. Parent-child retrieval works best when the parent itself makes sense. Now let's configure the hierarchy. We need two splitting strategies. The parent splitter creates the larger context units. The child splitter creates smaller search units inside each parent. For this demonstration, imagine we start with a parent around 2,000 tokens and children around 400 tokens. Those are starting values, not universal rules. Your best configuration depends on your documents, queries, embedding model, retrieval strategy, and evaluation results. The important relationship is what matters. Parents are large enough to preserve useful context. Children are small enough to represent focused ideas for retrieval. We'll test the actual sizes later instead of assuming one number works everywhere. Let's visualize the two stores. On the left, a vector store holds child chunk embeddings, small, fast to search. On the right, a document store maps parent IDs to full parent texts. When a query arrives, the vector store finds the best child chunks. Then each parent ID is used to retrieve the complete parent context from the document store. That context, not the tiny chunk, is what the LLM sees. Now connect the pieces. The retriever needs access to two things. First, the vector store containing the searchable child embeddings. Second, the document store containing the larger parent content. At query time, the retriever searches the children. Each matching child carries a relationship back to its parent. The system follows that relationship and returns the larger parent context. From the application's perspective, you still invoke a retriever. But internally, two different units are doing two different jobs. Children find, parents explain. Watch what happens at query time. The user asks about the notice period for termination. Internally, that query gets embedded and matched against child chunks to find the most relevant small snippet, but what actually comes back is the entire parent section. So instead of a 3-sentence fragment, the LLM sees the full section 4 with all its definitions and cross-references. The precision happened at the child level, the context arrived at the parent level. Let's follow one query from beginning to end. The user asks, "What is the termination notice period?" First, the query is embedded. The vector store searches the smaller child chunks. A child inside section 4 scores highly. That child contains a parent ID. The retriever follows that ID to the document store and loads section 4. Before generation, duplicate parent results can be removed. Then the relevant parent context is sent to the LLM. So the complete flow is query, child search, parent lookup, deduplication, generation. Understanding that pipeline is more useful than memorizing any particular framework API. Now let's see the same architecture in Dify. Inside the knowledge base settings, configure the document for parent-child chunking. You'll define a larger parent unit and smaller child units within it. For this demonstration, we'll start with example values so we can see the architecture working. But don't treat those numbers as recommendations for every dataset. What matters is what Dify does with them. The smaller child chunks become the precise retrieval targets. When one of those children matches a query, Dify can return the associated larger parent context. Then use the built-in retrieval testing tools to experiment. Try the same question with different configurations. Look at which child matched. Inspect the parent context that was returned. And ask, did the larger context actually improve the evidence available to the model? That's much more useful than simply turning on parent-child mode and assuming the default configuration is better. We're halfway through, so here's the checkpoint that matters. Could you explain this architecture to another engineer? There are two storage responsibilities. The vector store contains searchable child embeddings. Those smaller chunks help locate precise evidence. The document store contains the larger parent content. Once a child matches, its parent ID tells the system which larger context to retrieve. So, vector store finds, document store expands. If you understand why those responsibilities are separated, you understand the foundation of parent-child retrieval. Now we can focus on making that architecture production ready. There's another production issue you need to watch for. Suppose 3 highly relevant child chunks all belong to the same parent section. The vector search may return all 3 children. If you blindly expand every result, you could send the same parent section to the LLM multiple times. That wastes context window space. It increases token usage. And it can overemphasize one piece of evidence simply because several children from that parent matched. So after child retrieval, deduplicate the parent results. 3 matching children may represent 3 useful retrieval signals. But if they all point to the same parent, you usually only need to send that parent once. Here's the pattern. 3 child chunks match the query. Their similarity scores are 0.87, 0.82, and 0.76. All 3 point to the same parent, section 4. Instead of returning section 4 3 times, group the results by parent ID. Then return 1 copy of that parent. You still need a way to rank parent results. One simple strategy is to use the highest scoring child as the parent's representative score. Other ranking or aggregation strategies are possible depending on your retrieval design. The architectural principle is more important than the exact formula. Deduplicate the parent IDs before generation. Search can produce multiple child matches. Generation doesn't need multiple identical copies of the same parent. Before we move on, there's one useful extension you should know about. Imagine your knowledge base contains 10,000 contracts. The user asks, "Show me the termination clauses from contracts signed after January 2024. Semantic similarity alone doesn't capture that entire request. Termination clauses is a semantic requirement, but signed after January 2024 is a structured filter. A production retrieval pipeline can use metadata such as document date, department, customer, document type, region, or access level. The important part for this lesson is where filtering happens. First, narrow the eligible documents using the metadata constraint. Then search the relevant child chunks. Then expand the winning children into their parent context. So the pipeline becomes metadata filter, child search, parent lookup, generation. There are more advanced ways to automatically extract those filters from natural language questions, and we'll cover that separately. For now, remember this. Parent-child retrieval controls the size of the retrieval and context units. Metadata filtering controls which documents are eligible to be searched. They're different techniques and they work well together. Now let's talk about overlap. Imagine an important sentence falls directly across the boundary between two child chunks. Without overlap, the first chunk may contain the beginning of the idea, while the second contains the end. The information hasn't disappeared. But neither chunk may contain the complete semantic unit. That can make the passage harder to retrieve for queries targeting the full idea. A small amount of overlap can help preserve information near those boundaries. For example, you might test overlapping adjacent children by 50 tokens. But 50 isn't a magic number. More overlap creates more storage and more duplicate content. Too little may not protect important boundary information. So treat overlap as another retrieval parameter. Start with a reasonable value. Measure retrieval quality, then adjust it based on your documents. So how large should a parent chunk be? There isn't one universal answer. A larger parent gives the model more surrounding context, but it also consumes more of the context window and may introduce information that isn't relevant to the question. A smaller parent costs fewer tokens and stays more focused, but it may leave out information the model needs. So don't memorize. 1,500 tokens is the correct parent size. Treat parent size as a hyperparameter. Test several configurations. For example, smaller parents, medium parents, larger parents. Then compare them on representative queries from your own dataset. Measure whether the system retrieves the necessary evidence. Measure how much irrelevant context gets included. Measure answer quality, and measure token cost. The correct parent size is the one that performs well for your workload, not the one somebody gave you in a tutorial. Here's your second checkpoint. What is the perfect child size? The perfect parent size? The perfect overlap? There isn't one universal answer. Those values depend on your documents, queries, embedding model, retrieval configuration, and the kind of answers your application needs. So treat them as parameters to evaluate. Test different configurations against representative questions. Measure whether the correct evidence is retrieved. Measure whether the returned parent contains enough useful context. Measure answer quality. And measure the additional token cost. The engineering lesson is simple. Don't tune RAG by intuition alone. Measure it. Before you move parent-child retrieval into production, check these areas. First, meaningful parent boundaries. Whenever possible, align parents with document structure or coherent semantic units. Second, persistent storage. Don't rely on an in-memory parent store for a production system that needs durability and scale. Third, parent deduplication. Multiple child matches shouldn't automatically produce duplicate parent context. Fourth, embedding consistency. The embedding configuration used for queries must be compatible with the vectors stored in your index. And fifth, evaluation. Benchmark the pipeline before and after every meaningful retrieval change. For retrieval, measure whether the correct evidence is actually being found and ranked. For generated answers, evaluate whether the response is correct, grounded, and supported by the retrieved evidence. Production RAG isn't about finding one configuration that feels right. It's about measuring whether your retrieval architecture actually works. So far, our queries have been self-contained. Real conversations aren't. Imagine the user first asks, "What are the termination clauses?" The system answers. Then the user follows up. "What about the notice period?" If you send only that second question into retrieval, the system may not know what the notice period refers to. One common solution is query rewriting. A lightweight rewriter, often a small LLM call, receives the relevant chat history plus the follow-up question. Its job is to produce a standalone retrieval query. For example, what is the notice period for terminating this commercial lease? That rewritten query then enters the same parent-child pipeline we've already built. Search the children, identify the matching parent, return the larger context. The retrieval architecture hasn't changed. We've simply given it a better question. So does parent-child retrieval actually improve RAG? It can, especially when the information needed to answer a question spans more context than the ideal retrieval chunk contains. But don't assume it will automatically beat standard retrieval on every dataset. Run the comparison. Create a representative evaluation set. Ask the same questions using your standard chunking pipeline. Then run them through parent-child retrieval. Compare retrieval metrics. Did the correct evidence appear? How highly was it ranked? Then compare the generated answers. Are they more complete? Are they grounded in the retrieved evidence? Did token usage increase? That's the real test. Parent-child retrieval is an architectural option. Your evaluation tells you whether it's the right one. Here's a failure mode that can quietly destroy retrieval quality. You create the child embeddings using one embedding model. Later, someone changes the query-side embedding model without rebuilding the index. Now your stored document vectors and query vectors were generated using different representations. The retrieval system may still run. You may not get a dramatic error message. But retrieval quality can degrade severely because the vectors are no longer comparable in the way your index expects. So treat the embedding configuration as part of the index itself. Version it. Record which model created the embeddings. Validate that configuration when the application starts. And if you intentionally change embedding models, rebuild and reevaluate the index. You don't necessarily need a separate document store to represent parent-child relationships. A graph database can model that hierarchy directly. Imagine child nodes connected to parent section nodes. The retrieval layer identifies relevant children. Then the graph relationship tells you which parent each child belongs to. You can group the matches by parent, deduplicate them, rank the resulting parents, and retrieve the larger context. This is useful when your architecture already stores document structure or relationships in a graph. But keep the concepts separate. Using a graph database doesn't automatically make a system, GraphRAG. Parent-child retrieval describes how smaller retrieval units map to larger context units. GraphRAG generally introduces graph relationships as part of the retrieval and reasoning strategy. They can work together, but they're not the same thing. During development, keeping parent documents in memory is convenient. It's fast, it's simple, and it's perfectly reasonable for proving that the architecture works. But now imagine deploying the application. The process restarts. What happens to your parents? You add a second application instance. How do both instances access the same documents? Your knowledge base grows dramatically. Does loading everything into application memory still make sense? Those are production questions. At that point, you typically need durable, shared storage appropriate for your architecture. The lesson isn't, never use an in-memory store. It's, use prototype infrastructure to learn quickly. Then replace it when your reliability, scale, and persistence requirements change. Here's one advanced idea before we wrap up. You don't necessarily have to use parent-child retrieval for every question. Imagine a knowledge base containing long technical manuals. A user asks, "What port does this service use?" A small standard chunk may already contain the complete answer. Expanding that result into a large parent may add tokens without adding useful information. Now consider another question. What conditions must be met before this service can fail over? That answer may depend on several related statements in the same section. Larger parent context could help. Advanced RAG systems can route different queries to different retrieval strategies. That routing might use rules, a classifier, or a model. But don't start there. Start with one strong retrieval baseline. Measure where it fails. Then introduce routing only when your evaluation shows that different query types genuinely need different strategies. Let's lock in the 3 things that matter most. Number 1, the best unit for retrieval isn't always the best unit for generation. Search smaller child chunks for precision, then return larger parent context when the answer requires it. Number 2, parent quality matters. Use meaningful boundaries and deduplicate parent results before sending context to the LLM. And number 3, don't memorize magic numbers. Parent size, child size, overlap, top K, and other retrieval settings should be evaluated on your own documents and queries. Remember those 3 principles, and you understand parent-child retrieval at the architecture level. Parent-child retrieval gets you the best context once you've found the right chunk. The next frontier? Making sure you find it in the first place. Multi-query retrieval rephrases your original question into multiple angles, catching answers a single phrasing misses. A quick bridge. Take your parent-child retriever and run it against each rephrased query. Then deduplicate the parent contexts by max score, exactly the technique you just learned. In the next video, we'll implement that end-to-end. Subscribe so you don't miss it, and I'll see you there. Parent-child retrieval is useful, but you shouldn't automatically add it to every RAG system. Imagine your knowledge base contains short FAQs. Each question and answer is already a complete, self-contained unit. Or maybe you're retrieving individual support tickets, product descriptions, or structured records where each searchable item already contains everything the model needs. In those cases, expanding every match into a larger parent may add complexity and tokens without improving the answer. Parent-child retrieval becomes especially useful when 2 conditions are true. The smaller unit is better for finding the evidence, but the larger unit is better for understanding the evidence. That's the decision rule. Use parent-child when the best unit for retrieval is smaller than the best unit for generation. Now let's test the architecture instead of assuming it's better. Take the same document, use the same query, and compare two retrieval strategies. First, standard retrieval. Look at the chunk that comes back. Does it contain the evidence? Does it include enough context to answer correctly? Now run the same query through parent-child retrieval. Look at which child matched. Then inspect the larger parent that gets returned. Did the additional context include something important? Did it also introduce irrelevant information? How much larger is the context? That's what side-by-side testing should show you. Not simply, parent-child returned more text. The question is, did returning more context improve the answer? Final checkpoint. You're designing a RAG system. How do you decide whether parent-child retrieval belongs in it? Ask one question. Is the best unit for finding the evidence smaller than the best unit for understanding the evidence? If yes, parent-child retrieval is worth evaluating. Use the smaller child to locate the information, then retrieve the larger parent to provide the surrounding context. But if each searchable unit already contains everything the model needs, like a short FAQ or a self-contained record, adding parent-child retrieval may only increase complexity and token usage. That's the decision framework I want you to leave with. Not, parent-child retrieval is always better, but I know what retrieval problem it solves, and I know how to test whether my system actually needs it. Here's how this becomes a career skill. Imagine an AI engineering interview. The interviewer says, "Our RAG system retrieves relevant passages, but the answers keep missing important surrounding context. How would you troubleshoot it?" A beginner might say, "Use bigger chunks." But now you can give a much stronger answer. First, evaluate whether the retrieved evidence is actually correct. Then inspect the document structure and chunk boundaries. Determine whether small chunks improve retrieval but lose necessary context. If they do, consider parent-child retrieval. Then evaluate parent size, child size, overlap, deduplication, metadata filtering, and ranking. Finally, compare the new pipeline against the baseline using a representative test set. That's an engineering answer. You didn't memorize a chunk size. You diagnosed the retrieval problem, selected an architecture, and explained how you would prove that it works. That's the skill employers care about. Here's your quick start guide. 1. Build parents around meaningful document units whenever possible. 2. Create smaller children inside those parents for precise retrieval. 3. Experiment with overlap when boundary information is hurting retrieval. 4. Deduplicate parent results and keep your embedding configuration consistent. 5. Evaluate the pipeline against standard retrieval before deciding it's better. And remember the principle underneath all 5. Search with the unit that retrieves best. Generate with the amount of context the answer actually needs. That's parent-child retrieval. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.